So refraction is the redirection or the bending of light, making light have a slightly different trajectory because light is passing through a different what we call medium. For instance, glass instead of air, or water instead of glass, that sort of thing. So refraction is light being redirected or bent, its trajectory is changed as it travels, leaves one medium and travels into a different medium. Now we're going to first focus on refraction in which all colors of light stay together. They're all bent the same. But here in a minute we're going to switch gears and we're going to talk about how a prism uses the phenomenon called refraction, the same phenomenon, and different colors of light are bent differently. So let's look at refraction, in which all colors of light are redirected or bent the same. We don't break out your Roy G bit, okay? So the example we're going to look at is light going from air, see this word air up here, traveling from air into water. And notice that for each one of these incoming packets of energy, for each one of these incoming rays of light, notice that it is bent or redirected a little bit. It's swinging, what we say, towards the normal. Here's the normal. Remember, that's the perpendicular kind of I drew a little bit ago. It's being jerked towards the normal. That'll always be the case, that type of bending or that direction of bending, as you're moving from something where light moves faster in air and light moves slower in water. And if that's the case, it's going to be bent towards the normal. So refraction, the redirection of light. So we say light is bent. It has a different trajectory. I'm going to show you an example of a couple examples of refraction here in a minute. But I think your author does a neat kind of analogy. If you think of you're driving a car and you fall asleep, and instead of driving on the pavement, you're going to kind of veer off onto the shoulder. Now those are different mediums, right? The pavement, your car is going to go one speed, and on the shoulder, which is most likely gravel, your car is going to go a different speed. So as you start to transition from one medium to the other, what's going to happen is that your right wheel, if you're driving in America anyway, if your right wheel will kind of slow down before your left wheel will. And so for that, can you kind of feel yourself, kind of your trajectory will change. So you'll be kind of veered off. As you change medium, you'll kind of veer off to the right. And that's what happens as light goes from one speed, traveling in air, to a different speed, traveling in water. It veers a little bit. It redirects. Now this is kind of a fun little experiment that you can do, showing you refraction of a pencil. So the way this works is we have a pencil in water, okay, and notice that we have air here, obviously, and water here. And here is your pencil. Okay, so the deal is that pencil is actually sending light information in all directions. Okay, so here we go. Here's light information coming from the tip of the pencil up. Now here's the refraction part. As it leaves the water, okay, so the actual path of the tip of the pencil light is there. As it leaves the water, notice it is bent away from the normal. I'm having a hard time drawing the normal here. It's bent away from the normal, and so actually, if you put your eyeball up here, okay, here's your eyeball in this figure. When you're looking down at the tip of the pencil, it appears its trajectory as it leaves the water is like this. So if you backtrack down here, it looks like the pencil is right here. And this is one that sometimes I'll kind of walk around the class and show them that a pencil looks bent if you look down into it at an angle in water. So this is what it looks like, and this is what it is. Okay, so that's light being refracted. A practical example, this is one that may kind of catch you off guard, is that actually the different densities of air, so remember we talked about how air is most dense here at the Earth's surface and is least dense up here, and we're going to see that light travels at a different speed when the air is different densities. It travels fastest up here, and light travels a little bit slower down here. I know it's both air, but okay. So what that does basically is the light, light information from the sun shining in all directions. Actually, this light information you see, instead of going along like this, is actually bent. See the refraction? See the kind of the gradual, it's not abrupt, it's kind of a gradual changing, redirecting. So the consequence it has is by the time that light from the sun, the original light from the sun, is refracted, it kind of has this sort of angle. And going back up into the sky then, even though the sun is there low on the horizon, here's where it appears. This is its apparent position because of refraction, because the light is bent. And why is it bent? Because of the different density in the Earth's atmosphere. Kind of cool, kind of cool. Actually, we have now two mirages, and both mirages have to do with refraction. We're going to start with Inferior Mirage, and this one is the most common one. This is one, well, you'll see it here in a minute. Inferior mirages count on air being different temperatures kind of quickly. And if you kind of read the description, the conditions that give you an inferior mirage, what you're going to read is, this is my Earth's surface, and what really works well is if this is concrete, and if the sun has been beaming down all day, this gets very hot. So hot concrete is great for inferior mirages, i.e. driving down the road. So what happens now is we have an extremely hot air here, and it cools off relatively quickly. And the reason it's so darn hot has to do with the concrete heating up and then heating the air right above it. So we have what we call a very steep cooling from the very hot surface to just a little bit above. And it will actually then, light will be bent. Light from objects will be bent, and they appear to actually be down below the horizon when they're really above the horizon. Okay, so I'll show you the example here. So for instance, here's a guy looking at a palm tree, and this palm tree is sending light information in all directions. So honestly, don't be too confused, because this guy actually does see the palm tree there. But notice that the information, the light information from the palm tree that's being sent down here, because this is so hot, unusually hot, you know, it's usually warmer and it cools down as you go up in the troposphere, but it's so very hot, what happens then is that the air is bent. Notice that the air is bent up towards the cool air. So instead of that information just kind of going down here, what happens is that information actually is swooped up, okay? And as it's swooped up, when it reaches the dude's eye, this last known trajectory of this light from the palm tree looks like it is down here. So actually he sees two palm trees. He sees the normal one, and then he sees an upside down one here. This is called an inferior mirage, below the horizon. Kind of cool, kind of cool. The second type of mirage is called a superior mirage, and superior mirages won't be below the horizon, they'll be they'll be above the horizon. So actually we're going to see that superior mirages look like they're hovering instead of being below the horizon. So superior mirages need actually a scenario in the Earth's atmosphere near the surface we call a temperature inversion. So remember what a temperature inversion is as you go up in elevation in the troposphere, it gets warmer. Okay, that is an inversion. So we can get temperature inversions in the polar regions, especially. And actually, I'm going to show you a temperature inversion of warm air kind of settling over a cold ocean. And then again, the difference between, in this case, the bit of, how do I say, the bit of cooler air below the warmer air, and then of course it gets cooler again after the temperature inversion, that the presence of this sort of situation actually is what bends the light, refracts the light, and makes these objects appear to hover above the horizon. So objects with in a superior mirage will appear to hover or loom above the horizon. So the example I have here is a ship. And one of the things we know about water is that large bodies of water, like the oceans, is that they are stubborn to heat up, and once they're warm, though, they're stubborn to cool down. So let's just say that the water has because it's lag time to warm up, it basically has created a pocket of cool air here. Okay, and then let's say we have warmer air above it because it's just kind of the air warmed up more quickly than the ocean did. So this is a temperature inversion, isn't it? As you're going up in elevation, the air is getting warmer. There's your temperature inversion. Okay, here is the bending of your light, the refracting, of the image of that ship. So that ship is sending out an image in all directions. One of the directions that ship is sending out, and our observer is going to be over here, is in this direction. So be assured that whoever the observer is over here sees the ship on the water. But this light that was sent in this direction was refracted back down, and notice its last known trajectory is right here. So here you go. If we take this back, they also see a ship hovering in the air. Isn't that cool? That's so strange. Okay, that's a superior mirage. Notice the horizon is down here, and you see you see the object, and you see a hovering object. Isn't that neat? That's called a superior mirage. So inferior and superior mirages. I mentioned that inferior mirages are, concrete is great for getting really hot, really heating the air up. And so we have a very steep, what we call temperature gradient, whereas you go up in elevation, the troposphere, it changes its temperature greatly. And so what that does is to take images like this car and refract them, or you see a second image upside down below the horizon. And actually, if you kind of look closely, you can see these trees. Actually, it looks like there's that sign. This looks like someplace in Iowa, doesn't it? So the example of a superior mirage I brought in was this, where if you look closely in the distance, you'll see these mountains here, and then you'll see another set of kind of mountains looking like they're hovering. That is the superior mirage. One of the things that I'm still looking into, or I want to have explained more fully, is, to me, the images that I've seen, like if you look over here at the floating mountain, the superior mirage, it looks like the mountain range, looks like the image is inverted. And what I've read is that the image is supposed to be right side up in a superior mirage and upside down in an inferior mirage.